Hello and welcome back to another coding session with Mr. Jacob. In the last video, we implemented a shell console renderer for our PixelLoop engine. As you can see there in the background, the rectangle that we are moving around in our PixelLoop engine is rendered here to my shell using ANSI color codes and ANSI movement commands. And even though this is actually quite fluid, today we want to try and optimize rendering output a little bit before we are using one of the next sessions to then really implement something useful with it. So what I want to do today is I want to get a glimpse at how fast this currently is, and we will see how fast we can get it by maybe optimizing the output of the needed ANSI codes to render this to the terminal. Beforehand this video, I did actually something to our code. I implemented a very quick and dirty way, let me see, to be able to run this simulation for this rendering for 5 seconds and collect the amount of frames rendered in this time, and then quickly calculate the time difference and calculate how many frames we actually rendered per second in this 5-second interval. So I've used the feature and CFG macro for this, so that I can simply, or should simply, be able to say features, and then I should be able to put how did I call it? Benchmark FPS here, and press enter. And when I run this now, it should actually only run for 5 seconds and then display stats. And as you can see, we are getting exactly that information here. We rendered 682 frames in 5 seconds, which means we have about 136 frames per second. So let's do this again and let's see if this value is actually kind of the same overall. Yeah, 135 now, which is absolutely in the same ballpark. Just to get beginning to see in the end if we can make this simple example really faster. If it's really faster for more complex examples in the end, we will see, I guess. So yeah, let's get going, I would say. So let's go back to Visual Studio Code here and let's open up our cross-term canvas. And this is actually what we implemented the last time. Check the link in the upper right corner there, or check the video description for a link to the last video to see what we did there. Today we want to optimize this a little. And as you can see here, when we are seeing this render function in our code, we are always moving to the position 0, 0 of our terminal and then rendering the full terminal for each character in the terminal. So even all of this black space that we had around our moving rectangle is rendered over and over and over again. For each frame we are outputting that anew. And the primary optimization I want to do today is I want to implement a way to only update the regions of the terminal that actually changed. So the parts where the rectangle was the last frame and now needs to not be there anymore, and the regions where the rectangle wasn't the last time, which were black and now need the rectangle rendered. And of course I want this to be automatically detected for anything that we render to this canvas actually. Yeah, so let's get going. To do this, we actually need some kind of information about what was in the frame the last time. So we have our color buffer here currently, which stores the information that we are to render in this current frame when the render method is called. But what we need now is something like a previous buffer as well. So let's define that quickly. It's a vector of colors as well. And we will always store in there the last frame that we rendered, so that we actually have something to compare with when we are rendering. So let's initialize this previous buffer here with a vector as a color as well. And I guess maybe we could start with an RGBA in this case, so that we set the alpha to to simply 0, and let's do it with width by height as well here, exactly the same dimensions as the canvas before. Okay, and why we are actually setting the alpha value here is because I want to have this previous thing initialized with something that is definitely different from the base information we have here, so that every pixel that is then set with a different alpha value or a different color is definitely rendered the first time. Okay, so now let's store this thing here. So each time we have rendered something, I think we should store our previous buffer. So let's see, I guess we are doing self previous buffer copy from slice. And I guess we should be able to just put self buffer in there. Maybe we need a reference to that, I guess. Yeah, so this should actually copy all of our color information to our previous buffer once we are rendering. So now that we have this information, the previous buffer information, we should be able to compare the two and only create render patches maybe, so areas of the screen where we have a color patch that we then actually need to put there. And what I would like to do is I would like to combine those render operations into patches, so that we see, okay, we need to move to a specific position, and then we have a couple of different characters which we need to write. And once we have finished writing, so there is something or there isn't something, some characters anymore that need updating, we will store this patch and we will begin a new patch once we determine that there is another pixel there that needs updating. And then in the end, we can iterate through all these patches and update them, so that we minimize the usage of move ANSI commands, and that we may be even able to optimize this further in the end if we want to combine patches and stuff like that. We will see. So I guess what we will do here is we will need some sort of data structure for that. So I guess let's create this data structure here by maybe I guess calling it a patch. So we have a patch, and a patch is always, it has a position, and it will be using the ANSI codes from crossterms. So the position will be a combination of two U16 values, I guess. And then we need the data to be written to the screen. And we would have different possibilities here, I guess, to store that. But I think I want to store that as a simple string. Or no, I guess we will need to manipulate this all over. So maybe it's just a vector of U8s, and we can, let me quickly check. The cross term, I've already opened the documentation of cross term here because I thought that we need that, has this, how is it called? It's commands that they use, but they have an interface for, no, that's not it, cross term command. So it can write to writers, and I guess it's something with queuable command, exactly. And there is something, you can actually, they implement that, and the moment you import that, you have the queue command on all std.io writes. So std.out, for example. A vector of U8s, for example, implements std.write as well. So we can write to an in-memory vector representation as well. But there is something like, I don't really know, is there executable command, is it? Yeah. And this is the direct version. So it's not queuing and then flushing to this thing and stuff like that, but it's directly writing to the writer. It's immediately outputting. And this is exactly what we want there to use that. So I guess we will use something like data And I guess it will simply be a U8 in this case, because we directly want to generate the ANSI commands here and store them. Yeah, so I guess we have that patch. So then let's quickly implement a pubfn new for this patch, and it will return a self, and it will be self, and it will be position, and it of course needs to take a position u16 and a y u16, and this position will then be x and y, and we need data, which simply will be an empty vector in this case, I guess. Okay, so now we have this new function. Now the question is, what do we need with this patch later on? I guess we want something like pubfn apply, and I think that, as always, we want to input the writer into it where it should be applied. So let's do that. This will be a writer. So do we already have that here? Yeah, we have already imported that one. So we can go back here. So I guess we will simply have something like writer w, which will be a mutable reference to a writer, and it will return, maybe, yeah, it most likely will return a result, I guess, because writing could fail, and in this case we should return the proper error. What's its problem here? Takes 2 generic arguments. Yeah, because we didn't import use anyhow result, because it is currently using the default result of Rust. So we want our anyhow result. And yeah, exactly. Now, of course, we need to return OK here in the end. And I guess we want to do here, just to mark for us that we need to implement that. This function later on we will call to apply this patch to the corresponding writer. Okay, so what do we need as well? I guess we will need some function to add data to it, but maybe let's just implement things and go along, and then we will see what further methods we need here. So I guess what I want to do here now is I want to hide the cursor, and then I don't want to move it anymore. And this code, I guess we will somewhat reuse, but let's comment it out for now. In the end, we want to show the cursor again. That is perfectly fine. And we want to flush. Okay, so what do we want to do here in between here? Actually, what we want here is something like we need to calculate the slices somehow. So the patches, I mean. So let's do something like calculate patches. And this one should actually give us a list of patches, and then for patch in patches, we want simply do something like patch apply, I guess, and we want to shortcut out if it does not work, and apply we of course need to give our std out here. Okay, so now we need to implement calculate, I've of course written this wrong, calculate patches, but this method doesn't exist yet, so I would say let's implement it. So impl on our cross-term canvas, pubfn, or it doesn't even need to be public, calculate patches, there we go, and we want a writer here, writer of any type, and we will do writer is a mutable reference to a writer, and it will return a vector of patches. Okay, so I guess we need to start by having our empty patches array here, and I guess we can already return it in the end, return patches, so that the system is not screaming at us all the time. And now what do we actually need to do? We need most of this code, I guess, because what we need to do is we need now to iterate the buffer and generate the parts that have actually changed. So let's move that code here and then let's uncomment it, and then we can modify it according to what we need now. So what we definitely need here is a reference to self, and okay, so I guess we want to iterate the same way. We want to iterate always 2 pixels because we have 2 pixels per line using our Unicode block char, and we want to iterate through all the columns. That is okay. We want to get the color of our buffer. That is fine as well. We want to handle if we have an odd number of rows there, which is also fine. I guess this is the part that we don't want anymore, at least not like this. This we have to check out how to do it, and yeah, so I guess so what we need as well as not only the colors of y1 and y2, but what we need is the same information, the exact same information. Let's call it maybe py1 and p for previous, from the previous buffer. So here must be a previous buffer, and here as well, because we need to compare those values. Okay, so where would we actually create a patch? I guess we need to somewhere for outside of this loop store the current patch that we are working on, because there may be more than one character to be part of this patch, and then we need to add it to the same patch until a difference occurs. So let's call it current patch, and current patch would be an option of a patch, and we will start with a none there. And it's an option because it can be that it isn't currently there, because if we are processing multiple characters that are not rendered currently, we don't have an current, or better maybe say call it active patch. It's the active patch that we are currently working on. So yeah, so what we now need to do actually here is we have the previous value and we have the new value. What we need to do is we need to do something like, if the new value is not the same as the previous value of y1, or the y2 value, the new one, is not the same as the previous y2 value, then we actually need to to put this data, this more or less this here, into the new patch. Yeah, so I guess what we need to do is we need then to check if active patch is some, or no, better is none, because if it's none, we need to create it. So we can already say that we want to be able to mutate that, and we will be able to, we will need to mutate the patches array in the end, because we will add things there. So if it is none, then we don't have a currently active patch, so we need to create one. So then we have active patch is patch new, and we give it the current x and y coordinates, because that's the position where we start that thing, and we need it to wrap it in a sum, of course, because the type is an option. Okay, so what's the problem here? Arguments are incorrect. Yeah, definitely. So we need to cast them down to a U16, which shouldn't be a problem because we started our whole width and height calculation thingy based on the terminal height and width. This may actually overflow, but not if you use it nicely, I guess. Maybe we should check that, but yeah. Let's ignore that for now. Okay, so we are creating now the new active patch. So after that, we can actually get a mutable version of that. Yeah, so let patch equal active patch as mute. Nah, come on, as mute, and unwrap it to get the mutable reference out of it. Yeah. Okay. Because we have handled that, so we've created it essentially. If it's not there, we can definitely unwrap this here because there must now be something within this active patch. And now we can do something like maybe patch add 2-row pixel or something like that. Yeah, I guess. And then we will put in there y1 and y2. And I guess now we need to implement on the patch something like pubfn add 2-row pixel, and it gets essentially the upper one, which would be a color reference, and it gets the lower one, which is a color reference as well. And I would assume it returns a result because I guess it might fail. We will see in a second. Maybe we don't even need that, but I guess we will. And yeah, so the question here is, what's the problem here now? Found mutable. Oh, yes. We need add mute self here. Or what's its problem now? Yeah, we need to reference those. Okay. Okay, then let's see. How would we actually do that? We would essentially more or less use this code. So let's kind of steal it here. And let's see. So there. I just wanted to format this. Okay, thank you. Okay, so actually we are now not using this, but we are using self. Oh, we need self dot how did I call it? Data. And I want not execute, I want not queue, but execute. And we need to, that was the wrong button again. We need executable command for that. And then we can actually put this set colors in there, and we need to change those to upper. And we need to change those to lower. And this should be self data execute as well. So now actually we would be writing to our internal data structure the same ANSI commands that we used before, but only for this specific 2 pixels which are in this column. So I guess this should actually work. So we are doing that in case that the color does not match. Yeah, that's actually that the information from the previous and the active buffer do not match. Okay, so if they match, then we have the thing that either we have a currently active patch which has already data in it, then we need to store it in our patches array for later applying it, or we need to simply go on if there is none. So if active patch is sum, or then I guess we can do simply directly let sum patch equals, equals active patch. Or is it, yeah, we actually kind of want to take it out there. Is that how that works? Yeah, borrow this binding in the pattern to avoid moving the value ref. Yeah. I actually want that one, don't I? So maybe I really want to do something like active patch is sum. And if it is sum, then I actually want to do something like I want patches.push active patch take unwrap, I guess this should actually takes the value out of the option, leaving a none in its place. Yeah, that's exactly what I want. So I'm getting then an option T out here, which replaces the original active patch with none. And then I unwrap that to get the real value out of this option that I just retrieved. And then I can push that into patches because I really want to take it out there. I don't want to have it in there. I don't want to copy it or something like that. So if active patch is sum, then we are doing that. If we do not, if we have the same characters here. Yeah. Okay. That makes actually perfect sense. The only thing that we are not doing yet, I just thought about, is we are not positioning the patch, but I guess we will do that in the apply function, won't we? Yeah, okay. So we are not there yet. So now I guess I can maybe remove that. And now, yeah, the only thing that is still missing is the apply function of our patch. So because what we are doing here is we are calculating patches, and there is something that we might have missed there. An argument of mood is missing. Wait. Oh, calculate patches. Why does calculate patches take a writer? Does this make sense? Where does it need a writer? It doesn't. I guess I'm not sure why I have this. I guess you will know, or I will rewind the video later on and see why I did that, because now I'm interested in that. So I calculate the patches, and then I apply all of those patches. Okay, and there is no method apply on a patch. Wait, didn't we pubfn apply, and it is on a patch. So why? No method apply found for struct patch in the current scope. Oh, yes, that's the usual thing that I always forget. I don't put the self there, and then, yeah. Okay, so now we are at the part where we implement the apply, and I guess this must be put there as a mutable reference. Okay, nice. But now we can. Why is that? Because we are not capturing the possible error there, so let's do that. And now let's implement the apply function, which should actually be quite easy, because now we have a writer where we can actually use the queuing here. And this would be a cursor move to command, and it would take self position 0 and self position 1. By the way, is there a nicer way to put now our tuple into this? Something like self position, maybe? Is that something that would work? Let's see. No, I don't think it would. Yeah, no. Okay. It was worth a try. So now we are queuing the move to there, and then we need to queue the, what was it, print? Yeah. So we are queuing a print command and a command that prints the given displayable type. Yeah, but a vector of U8s is not directly displayable. So I guess, isn't there something like from UTF-8 or something like that? Yeah. And you can put a vector in here. So I would then solve data, put that in there. And I guess we need to reference this. And I would assume that this can actually fail, though. So we have this shortcutting out there. So what we are doing here is now we are converting that to a UTF-8 string that we can then print into the terminal output writer. I'm not sure if we can actually leave this one out and directly use that. We could, of course, use the write function on the writer directly, but I actually want to use the queuing because I'm not 100% sure if cross-term otherwise works 100% perfectly. So let's try it this way, and maybe that will be an optimization later on. So actually that should actually maybe already work. So we don't need to move to new lines anymore. We don't need to reset the color at the end anymore because now we are only working on blocks. Is that right? Yeah, I guess it is. At least as long as the terminal has the same size as the rendered canvas. Otherwise we might need a new patch. We might need a new patch at every new row. So maybe we want to limit patches to each row. So something like, where is it? So each time we are in this loop here. So we are actually in this one here. For each new line, if active patch is some, essentially we want exactly those lines here. So every time we are moving into the next line, we want to make sure that we have a new patch so that the characters printed out are actually then moved into the next line. Yeah, that makes sense. And actually, once we have finished all of that, we want the same there. So because there might be another active patch in the queue, the last characters have been updated, so then we need to push that actually into the patch vector that we return there as well. Okay, so should we give it a try? I guess we should give it a try. And yeah, maybe just run it without anything and let's see first. Okay, it does not compile. Where did we do an error? Add 2-row pixels. Cannot use the question mark operator in a method that returns back patch. What? Okay, let's see. Where's the problem? Actually, calculate patches returns. Okay, so I guess this can fail then. And the patch calculation, yeah, it definitely can fail. So we need to put it into a result. And then we simply wrap this one with an OK. And I guess then we need to shortcut out of the error here, should it happen. And now this should hopefully be okay. Yeah. I mean, it works for every other line, it seems, but it kind of does not. I've got an idea. Let's see. We are yeah, we are, as always, come on, we are iterating by steps of 2 line-wise, because we have 1 line for 2 lines of pixels. So 2 vertical pixels are sharing 1 line. And I think that when we create a new patch, where do we do that actually? It should be here somewhere, there. Yeah, then we are using the real pixel Y value. But what we actually need to do is we need to divide that by 2. Because we want the terminal, yeah, we kind of want the terminal row, and the terminal row is always half of the real pixel Y value. That's why we are skipping every other line in the output, I would assume. Let's see. Yeah, okay, this works. Okay, there is, okay. Now there is the cursor, which we are showing again at the end. As you can see it follows along our thingy there. So let's maybe move at the end of every render cycle. We could move to, let's see. I guess we could do something like std out q. Either we could let the have the cursor hidden there, have the cursor still hidden there, or we could, I guess, move to something like self dot width self dot height divided by 2. Maybe something like that. So we are just putting it down in the lower right corner for now. Yeah, as you can see now, it's down here. No, you can't see because my image is in front of it, but it's not in the area of this thingy here again. So now let's see. We have this features benchmark FPS, and before we had something like 135 frames per second or something like this. Let's see how many frames we can actually render now. Let's see. Let's see. Okay. 55,829 frames per second. Okay, I see. Yeah, that's only a little bit more. So what would actually happen, which was absolutely unusable before? Maybe we should have tested this with a very, very small terminal. So let's see how it's working out now. Okay, the initial fill is quite slow, but then the movement is working quite smoothly, and then I can't actually. Yeah, that's bad, because then I can't read actually the output. Okay, so let's try it with my normal terminal size, which I usually use when I'm not recording. So that's actually 20,000 frames per second. And it's, okay, that's massively faster, which is completely clear because it only needs to render this small section and update this small section here now with this box. So how could we actually check that? We could maybe quickly add that there are more boxes created which are being rendered to see how this is actually working out. So let me make this bigger again, and let's go back to Visual Studio Code, and let's go back to our main. And it has now in the state, it has box position, box direction, and box size. So let's maybe change that to, let's maybe have something like a struct box here. And the struct box could hold all of those informations. And then we simply have in the state boxes, which is a vector of box, And I guess we should give it a color as well, which is a color, and maybe a shadow color as well, which is a color as well, because we have this slight shadow there. So, and when we create this new state, I guess what we do is we simply take this out there, or maybe we should, I should move that maybe here for now, just to have the information there. And then we could have something like boxes there, which is, or maybe I could initialize this with the boxes that I need actually. Yeah, why not? Why not? So let's directly put the boxes in here. So we have one box there, which is the same one than it was before. Let's indent that and let's uncomment that, and then I guess it needs a color, which is then the color that we give it here somewhere. I'm not 100% sure where. There actually. During rendering we initialize the color. Okay, so let's put that color now into the box here. So that would be this one, this yellow color would be the normal color, and then we have the shadow color, which should be this one actually. And now let's refactor this rendering here. So in the update function, we need to do this for box in box self boxes. No, S boxes. Sorry, because it's in the state. And expected pattern is that maybe I cannot call this one box or something like that, because yeah, but doesn't it? I don't know, what's the problem here? Do I need it to an iter here? No, it's, yeah, it doesn't like the box name, the lowercase box. Okay, so but now I guess we need to simply update for each of those boxes here. So I guess the we need, actually we need a, don't we need something like a mutable iterator or something like that? It shouldn't actually, well, what we are doing here shouldn't actually be possible. Because we don't have a writable reference to boxes. Is there actually something like itermut? Yeah, that's exactly, that's what we need. We need a mutable iterator. Otherwise this will not work. But now we are actually iterating over all the boxes. We are updating their information, and then we go on. And here what we will do is more or less the same thing. So I guess we will now iterate for b in s.boxes dot iter. In this case, we don't need a mutable iterator because we only need to render those. We need to render those. So I wanted to format, and now I want to change all of those to a b here. And the same thing here. And then the color would be the shadow, of course. So b.shadow color and b.color. And if I've done this correctly, this should actually compile and do the same thing for now as before. So let's see. Okay, so this still renders our box. And it still has the 45,000 frames. We definitely need some sort of frame limiter in our PixelLoop engine. I guess we'll do that next because in cases like that, we need to render the, we need to limit that. It is perfectly reasonable in this case to limit the rendering speed to 60 frames per second, because currently we are just doing it as fast as we can, and this doesn't make any sense at all. Okay. But what we should be able to do now is we should now be able to add more boxes here, which should be able to move even in different speeds and stuff like that. So let me copy this box here, and then we can go ahead and put more of them in there. Maybe for now, let's put there like 4. So let me copy that again. Okay, so what we now want to do is we want to, I guess, change their sizes maybe. So I guess maybe one that is, oh no, that was the first box. I didn't want to change that. So this one maybe a smaller one, 5 by 5 maybe. Let's make it a square. Then we should maybe have a larger one like 20 by 20, and then maybe we could have a square 10 by 10 one. Yeah, why not? And then we need to give them different colors. So let's maybe change things up a little by doing something like that, and then making this one like this. And we could do something like this here, and maybe something like this. Yeah, and now the box position definitely needs to be something else than the default, because we want to kind of start them at different y coordinates, I guess. So they are all starting at 0, and this one maybe starts at, why not, 10. And this one starts at 0 and 23. And so that they have kind of a different moving pattern. This one starts at 0, 4, and this one starts at 0, 0 as it always did. And then we can maybe make this one move faster on the x-axis than on the y-axis. This one moves faster on the y than on the x. And this one moves faster on both axes. And then let's see, this should actually create a lot more boxes there. Yeah, and as we can see, we have that's actually quite nice. Okay, now I can't read my output. Oh yeah, and it's still 44,000 frames per second. Let me make this a little bit smaller there again, and let's try that again. And in the recording, this may seem to stutter, but actually it is not. That's something that I discovered in the last one. It's very fluent in reality, but it's in the recording, it kind of stutters. So yeah, now we have 20,000 frames, which is actually still quite fast. Yeah, I guess we have our first optimization here. I thought we may need another optimization, which we could actually quickly implement, because I was thinking about not updating the color information if it's not strictly needed. So if pixels next to each other have actually, when they are rendered the same color, we only need to output the color and not the character, and not the color information again. We could, let's maybe quickly implement that. Why not? So what would we need to do to have that? Our patch would have to hold some information on what the last character or the last pixel it added had as a color value. So previous colors maybe, because it's actually 2. It's the both pixels on top of each other. So I guess this would be an option of 2 colors. Yeah, I guess so. So yeah, let's actually quickly do this. Previous colors is none, and Now when we are actually adding the two row pixel, we need to only add this information here, this color information, if we either don't have a previous color, because in this case we are just starting and need to set the colors, or we have a previous color and it actually deviates from the colors that we want to print. So yeah, I guess we can simply write that out, can't we? So if self.previous color is none, or self.previous colors can I actually, I can't the problem here is I would love to do something like now, like do something like previous, come on, upper comma previous lower here, and just do it like that, but that actually does not work, because you can't combine this kind of syntax with this matching syntax with the normal if condition, unfortunately. But what is it complaining? This pattern has two fields, but the corresponding tuple variant. Oh, yeah, I just should have put further brackets around here, and then this should actually work. So yeah, I guess I might do it that way nevertheless. So I'm matching that. And if we actually match that, then we can... That's actually not very nice, because then we need to repeat all of this in two different branches. And I don't really want to do that. Let me think about that for a second. Okay, how could we actually do that? If self previous colors, can't we get a reference of that one? We can, and now we should be able to unwrap that. And can I do something like if if I combine those with self previous colors is none, or which should then only evaluate if it is some. So, and can I do something like if this is not equal, is that actually possible? Can I do something like upper lower here now? Is this actually something I can do? Is this it seems I can't compare color with color. So yeah, but if we actually wait, can I do something? Can I? Okay, that's kind of yeah. Okay, we will see if this works actually. So if this is the case, so if it's either if it's either none, so we don't have a previous color, or it does not match the previous color, then we want to put the data there, and otherwise we simply print the Unicode character. And then, of course, what we need to do, if it does not match, we need to do self previous colors equals a dereferencing of upper and a dereferencing of lower, which should actually copy the values, I would have thought. Oh, yeah, and we need to put that in a sum, and then we need to put braces there. Come on. Yeah, so that we update that. If we changed it, then we have another previous color. Okay, so let's see if this still renders. It seems to still render. So I guess it works, and it's nearly, oh, it seems even faster. It was 20,000-ish before, and now it's 21,000-ish, which is like 5% faster, which is quite a lot actually, if we can believe this enormous update speeds here. But it makes sense because all of this congruent color information that we have here now only needs one color ANSI character printed. So I guess maybe we will see it if it's, yeah, you can even actually see it quite well the moment the screen is actually created, because that was a lot slower. The initial coloring with black color was initially very slow and is now a lot faster. So yeah, that's actually really, really nice. So let's maybe just run it. Yeah, so we have successfully optimized that. We definitely need some sort of frame limiter there, but I actually really much like this is all flying around here in my terminal. That's a really nice thing actually there, and yeah, I like that. And I like that we optimized it in such an easy way, and it's that much faster. As I've said, we definitely now need something like a frame limiter or something like that within the PixelLoop engine that makes sense anyway. Before we had the frame limiting in the Pixels implementation, which used WGPU and stuff like that, and so was limited by the update rate of the monitor, the refresh rate. It automatically limited to this render and frame rate. But I guess now we need to do something like that in our engine as well if we want to. Or maybe we only do it in the cross-term canvas, but we should definitely do it. Yeah, so I hope you enjoyed this one as well. I definitely did. And I guess I will see you in the next one. Bye.